Assalamu alaikum. Today we want to talk about chapter 16, part 4, entitled Lewis acids and bases. Now, for a substance to be a proton acceptor, a bronzed lower base, it must have an unshared pair of electrons for binding the proton. As for example, in NH3, using Lewis structure, we can write the reaction between H plus and NH3 to form an H4 plus. Now, G.N. Lewis was the first to notice this aspect of acid-base reactions. He proposed a definition of acid and base that emphasizes the shared electron pair. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Now, for example, the reaction between NH3 and BF3 occurs because BF3 has an incomplete octet of electrons. It therefore acts as an electron pair acceptor, a Lewis acid, toward NH3, which donates the electron pair, as in this reaction. Now, other examples of Lewis acids are BH3, BAF2, BH2. Everything that is a base in the bronzed lower sense, proton acceptor, is also a base in the Lewis sense, an electron pair donor. In addition, many simple cations can function as Lewis acids. For example, Fe plus 3 interacts strongly with cyanide ions to form the ferricyanide ion. Now, the ion has vacant orbitals that accept the electron pairs donated by the cyanide ion. The metal ion is highly charged too, which contributes to the interaction with ions. Now, some compounds containing multiple bonds can behave as Lewis acids. For example, the reaction of carbon dioxide with water to form carbonic acid H2CO3 can be pictured as an attack by a water molecule on CO2, in which the water acts as an electron pair donor, Lewis base, and the CO2 as an electron pair acceptor, Lewis acids. As can be seen in this figure, here notice that water has the oxygen of water has lone pairs of electrons, so it attacks first of all one of the two bonds in between carbon and oxygen donates 2 electrons to the oxygen, so that carbon now has a vacant orbital, so that oxygen can attack here, and so the carbon can accept an electron pair donated by water, and then finally to form the carbonic acid H2CO3. So here water acts as a Lewis base, electron pair donor, and CO2 with multiple bonds can act as a Lewis acid and electron pair acceptor. Now, Lewis bases are defined as electron pair donor, as we said before. Anything that could be a bronzed lower base is a Lewis acid, and Lewis bases can interact with things other than protons, however. And this is the advantage of the Lewis definition of acid and base, that it allows us to treat a wider variety of reactions, including those that do not involve proton transfer as acid-base reactions. So instead, to avoid confusion, a substance such as BF3 here is rarely called an acid unless it is clear from the context that we are using the term in the sense of Lewis definition. Instead, substances that function as electron pair acceptors are referred to explicitly as Lewis acids. So here, Lewis acids include molecules that, like BF3, has an incomplete octet of electrons. In addition, as we said, many simple cations can function as Lewis acids, for example, Fe plus 3. Also, the hydrated cations we encountered in section 16.9, such as Fe H2O plus 3 in figure 16.16, form through the reaction between the cation acting as a Lewis acid and the water molecules acting as Lewis bases. When a water molecule interacts with the positively charged metal ion, electron density is drawn from the oxygen. This flow of electron density causes the OH bond to become more polarized. As a result, water molecules bound to the metal ion are more acidic than those in the bulk solvent. Now, this effect becomes more pronounced as the charge of the cation increases, which explains why +3 cations are much more acidic than cations with smaller charges. Now, this figure shows us a hydrated ion Fe+3 acts as an acid by donating an H+ to a free water molecule, forming H3O+, as you can see here. And this figure here shows us the acidity of a hydrated cation depends on cation charge and size. Here, the interaction between a water molecule and a cation is much stronger when the cation is a smaller ion of higher charge. Now, the pull of electron density toward the cation weakens the polar OH bond of water molecule and allows the transfer of a proton or H+ ion to a nearby water molecule. As a result, hydrated cations tend to be acidic, with their acidities increasing with increasing charge and decreasing size. And this figure explains that here we have weak electrostatic interaction, and also here weak shift of electron density. Here we have lower charge and higher size, whereas when we have higher charge and lower size, we have strong electron interaction, and we have here strong shift of electron density, as you can see here. In conclusion, the Lewis concept of acids and bases emphasizes the shared electron pair rather than the proton. A Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. Now, the Lewis concept is more general than the Bronsted-Lowry concept because it can apply to cases in which the acid is some substance other than H+. Now, Lewis acids and bases can be described as hard or soft, and we have here examples of مثلا Lewis acids. H+ is hard, K+, Mg+2, Fe+3, Bf3, CO2, SO3, R, MgX, AlCl3, Br2, and here we have soft Lewis acid, Ag+. Examples of Lewis bases: OH-, F-, and then we have water and ammonia as hard Lewis bases, SO4-2, then we have H-, and CO here is soft, Pr3, C6H6. Now let's look at this sample integrated exercise, putting concepts together. Now, phosphorus acid here has the following Lewis structure. Explain A. Why H3PO3 is diprotic and not triprotic. So let's start explaining. So in A, acids have polar HX bonds. Now, from figure 8.6, we see that the electronegativity of hydrogen is 2.1 and that of phosphorus is also 2.1. Now, because the two elements have the same electronegativity, the HP bond is nonpolar. Thus, this H here that is attached to phosphorus cannot be acidic. Now, the other hydrogen atoms, however, are bonded to oxygen. You see here, bonded to oxygen, which has an electronegativity of 3.5. So, the OH bond dipole are therefore polar, with H having a partial positive charge. These two H atoms are consequently acidic. Now, in B, A 25.0 ml sample of solution of H3PO3 is titrated with 0.102 molar NaOH. It requires this volume of NaOH to neutralize both acidic protons. What is the molarity of the H3PO3 solution? And then in C, the original solution from part B has a pH of 1.59. Calculate the percent ionization and Ka1 for H3PO3 if Ka1 is much greater than Ka2. D. How does the osmotic pressure of a 0.05 molar solution of HCl compare qualitatively with that of a 0.05 molar solution of H3PO3? Explain. So here, to start answering B, we must put the chemical equation for the neutralization reaction. You see here, 1 mole of H3PO3 is stoichiometrically equivalent to 2 moles of NaOH. Remember this as we start to continue the solution from the definition of molarity. Molarity equal moles per liter. We see that number of moles equal molarity times volume. Thus, the number of moles of NaOH added to solution, this times this, and this is the number of moles of NaOH. But from the balanced equation indicates that 2 moles of NaOH is consumed for each mole of H3. Thus, the number of moles of H3PO3 is, in the example, is this, you see, times 1 divided by 2. And this is the number of moles of H3PO4. Now, the concentration of H3PO3 solution, therefore, equals this divided by the volume in liter and the 0.0476 molar. This is the concentration. Now, for part C, from the pH of the solution, 1.59, we can calculate the equilibrium. Then H plus بتساوي anti-log this, and this is 0.026 molar. Now, because Ka1 is much greater than Ka2, most of the ions in solution are from the first ionization step of the acid, which is this. Because one H2PO3 minus ion forms for each H plus ion formed, the equilibrium concentration of H plus and H2PO3 minus are equal. So these are equal and equal to this number. Now, the equilibrium concentration of H3PO3 equals the initial concentration minus the amount that ionizes to form H plus and H2PO3. So this 0.0476 minus 0.026 equal 0.022 molar. These results can be tabulated as follows. You can hear initial. This is initial 0, 0. The change is this minus plus. And then the equilibrium, we have this, this, and this. And then we can calculate the percent ionization is molar concentration of H plus at equilibrium divided by H3PO3 initially times 100%. And this will equal, as you can see, 55%. Now, the first acid dissociation constant is Ka1 concentration of products divided by reactant from the previous equation, and we get this value, 0.031. This is the value of Ka1. Now, for part D, we learned that osmotic pressure is a colligative property and depends on the total concentration of particles in solution. Section 13.5, remember? And because HCl is a strong acid, a 0.050 molar solution will contain 0.05 molar H plus aqueous and 0.050 molar Cl minus, or a total of 0.100 mole per liter of particles. Because H3PO3 is a weak acid, it ionizes to a lesser extent than the HCl, and hence there are fewer particles in the H3PO4 in the H3PO3 solution. So as a result, the H3PO3 solution will have the lower osmotic pressure. End of part 4 and chapter 16. Thank you.